see if it goes through. Better turn your mic off.
Oh, yeah, right. Good evening, everyone. Welcome back. It is our November Speakers Night for 2025. Welcome to RASC Toronto Centre. We are online tonight, and I am Dr. Elena Hyde, the second Vice President of the RASC Toronto Centre. Welcome, everyone, to our Speakers Night presentation. Please note that this meeting is an online-only presentation and not at our new York University meetup spot. And just as a reminder, this is in fact our last meetup for 2025, as we will not be having a broadcast in December. So we'll find you again in 2026. Now, later on, we'll have a few announcements about various programs for Ask Toronto Centre. But first, of course, we have a Speakers Night event to kick off. And per usual, I'm going to go ahead and start with our land acknowledgement for the Rask Toronto Centre. And I'll begin this by acknowledging that the Royal Astronomical Society of Canada Toronto Centre meets on the traditional territories of many Indigenous nations, including the Haudenosaunee Confederacy, the Huron-Wendat, the Mississaugas of the Credit First Nation, and other Anishinaabe peoples. These lands are part of the Dish with One Spoon Treaty and are now home to many diverse First Nations, Inuit, Métis, and Indigenous peoples from across Turtle Island. As we engage in astronomy here together, we respect, learn from, and honor the deep relationship between Indigenous peoples, the sky, and the earth. Now, to get into our speakers night for this evening, I'm very lucky to be able to introduce a really interesting, almost rocky, you might say, talk. A little bit of rock and roll here for our last talk of the year. We're lucky to have Dr. Charles-Édouard Boukaré, an astronomy professor at York University. His research focuses on all kinds of cool stuff about planets, and especially rocky planets, deep interior structure, looking at planetary sciences, and of course, probably the Earth. He might tell you a little bit more about that. All kinds of cool fluid mechanics, mineral physics, great stuff like that. He's got lots and lots of degrees. He's got dual master's degrees in engineering, geology, and planetary sciences from France. He's done his PhD in geophysics, and he's done postdoctoral research at Brown University, I believe, in the US, that is, but also in Switzerland, in France, and here in Canada. He's been an assistant professor at the Department of Physics and Astronomy at York University here in Canada since 2023. And he's particularly known for his work on magma oceans and mantle dynamics. So maybe we'll see some of that tonight. Over the past 8 years, he's done lots of computational models and looked at early evolution of Earth, the Moon, Mercury, exoplanets, and all kinds of really cool stuff. He was actually awarded the prestigious International Dornbos Prize for outstanding contributions to the study of Earth's deep interior. So, mysterious place. And tell us if there's any secret worlds under there. Now, this is the part of the introduction where I would usually ask our speaker to take us up, and away. But in this case, I think I will just say, let's rock and roll. Over to you, Dr. Boukaré.
Okay. Good evening, everyone. Thank you very much for being with us. Thank you very much, Elena, for the introduction. It's really a pleasure for me to be here with you guys, well, online. It's always a pleasure to talk about planets. So today I'm going to talk about, yes, rocky planets, both in our solar system and a little bit beyond. So we're going to talk about exoplanets. And we're going to also briefly discuss a little bit of my research at the end of the presentation. And of course, please ask any questions that you may have either in the chat, or you can also save your question for the end of the presentation. We're going to have, I believe, some time to chat together. Okay, so I'm going to start this presentation. So we're going to talk about the structure, composition, and dynamics of rocky planets. So I'm going to start with this slide, because as you may know, we are actually living a very exciting time right now. because it's the first time in humankind that we can not only observe planets beyond our solar system, but we are actually currently characterizing them. What I mean by characterizing is that we can measure their average density. We are close to measure maybe the compositions of their atmosphere. So it's extremely exciting for not only astronomers, but also geologists. So as Professor I just mentioned, I'm actually trained as a geologist. And so it's also an interesting time in the scientific community because for the first time now, geologists have to discuss with astronomers. And as you can imagine, it can create a lot of tensions, but this is constructive tensions that I would describe. So this raise important questions, and I'm going to discuss one of them in a second. First of all, I would like to emphasize the fact that we're going to talk about only rocky planets today. So here in this picture, you see some kind of statistics on the exoplanets that have been found so far. We have giant gas giants, so planets made mostly of gas, like Jupiter, that represents 30% of the planet that has been found so far. You see that terrestrial planets, or rocky planets like the Earth, they only represent 4% actually of the population that has been observed. Super Earth planets, that are rocky planets, that are actually larger than the Earth, but in terms of structure and composition, we believe they are similar. We're going to talk about those two today. And Neptune-like planets, actually, we don't know much about those. We believe they are actually some kind of intermediate object between maybe rocky planet and gas giants, but it's still not clear what they are. So we're going to talk today about terrestrial planets, rocky planets, and super Earth planets. And you see this represents already 35% of the planet population. So now I would like to move to something that is that I believe is extremely important when we want to understand how planet works and how we want to describe them. It's even more important in this context where geologists, who are used to have a lot of data to describe an object, have to talk with astronomers. We are working hard to get a small amount of data because, of course, they are not dealing with the same constraints. So what I would like to explain today is, or to maybe emphasize, is what I call the level of description of your model, and the level of description of your model must match the level of detail in the data. So as you can imagine, the amount of data that we're going to have to characterize exoplanets will not be the same as the one that we have to characterize planets in our solar system. So we can distinguish the zeroth order. This is what would be the most basic description that you can do on a planet. And we can say that this would be the average density of a planet. So if you can measure the mass of the planet, the size of the planet, you can then determine the average density. And with this average density, you can distinguish the rocky planets, so what we just discussed before, from a gaseous planet. The gaseous planets would have a much lower density. But with only this information, it would be very difficult to go in more detail. So this is a current challenge of the exoplanet community. We would like to maybe use what we know from the solar system to better predict or anticipate what are behind those data that we have from astronomy. Then we have the first order of the description. This is, so in the context of planets, this will be relevant for rocky planets in our solar system. We have access to a bit more information because we can send spacecraft or orbiters that can do some kind of remote sensing observation. We actually can observe those planets from the ground with ground-based telescopes. So we have definitely more data. We can characterize the surface, for instance, count the number of craters. We can actually measure also the composition. So with this, we can, of course, constrain a bit more the planet, the state of the planet. And ultimately, you have, the second order or even higher order of description. This will be valid in the context of planet only for the Earth. where we actually live on the planet. So we have access to rocks easily. We can walk, to mountains, get a rock, analyze a rock in the labs with very fancy apparatus. We can investigate the interior, as we're going to discuss in a second, with different techniques. And so, of course, you will be able to describe the interior of the planet with a much more higher level of description. I wanted to discuss this because I'm going to articulate my presentation today around those different levels of description. Because this is a challenge, again, in the exoplanet community. It's a challenge because even though for exoplanets, we know only the 0th order, we still have access to planets in our solar system and Earth. So we can maybe anticipate a few things based on what we know in our solar system. So in this presentation, I will discuss the structure, the composition, and the dynamics of planets from the lowest order of description, so this would be the basic order, to the highest level. And the highest level would be always applied to the Earth, because we can do this only for the Earth. So this is also a way to illustrate different fields in planetary sciences or geophysics that would be specifically dedicated to those tasks. So for instance, the structure of a rocky planet, that would be the first part, is determined by seismology. This is our best way today to determine the interior structure of a rocky planet. Then to think about the composition of a rocky planet, the specific field that study this is geochemistry or mineral physics. So we're going to talk a little bit about this today. And then the last key ingredients that we need to understand planets or the interior evolution of planets is fluid dynamics, or more specifically geophysical fluid dynamics. And we're going to talk a little bit about this, and I'm going to introduce maybe the most advanced models of planetary interior dynamics that we can use as a guideline to maybe predict what would be the behavior of rocky planets beyond the solar system. Finally, I'm going to discuss briefly my current research on exoplanets. And you will see I will focus on a very specific class of exoplanets, and to give you an idea of what is the current state of research in exoplanets. Okay, so let's move to our first part. We're going to discuss the structure of rocky planets. Actually, I said here the Earth because we're going to go from low to a high level of descriptions. And this is seismology that would give us the most detailed view or detailed description of planetary interiors. So, first order structure of rocky planets. A rocky planet is composed of actually two main envelopes. If we neglect for now the atmosphere, that would be relatively thin compared to those two envelopes that I'm going to mention. We have the mantle made of rocks, and we have the core made of metals. For some planets, like the Earth, you have a molten part of the core, so the outer core is molten, and the inner core is solid. For all rocky planets in our solar system, the mantle is 99% solid. So if there is a few things that I want you to remember in this presentation, is that the mantle of rocky planets in our solar system is solid. Because for some reason, we all learn in high school that planetary mantles are some kind of magma, and we live on top of a big pool of magma. This picture is actually very wrong. The mantle of the Earth, for instance, is at 99% solid, and except in very few regions in the Earth's mantle, where the temperature is high enough to generate magma and then create volcanoes at the surface of the planet, the vast majority of the mantle is solid. So this is the zeroth order description of the structure of rocky planets. Of course, I've shown here below some example of rocky planets that has been observed beyond our solar system. You see that some of them are significantly larger than the Earth. And the challenge today in our community is to determine what is the interior structure of those planets. For instance, do they have a solid core? Do they have volcanoes activity that would allow interactions between the interior and the atmosphere? Those are current questions that we have in the field. But of course, we have a much more detailed picture of this interior. So now I'm going to show you a movie, a video that describe the interior structure of the Earth's mantle as seen by seismology. So seismology uses seismic waves to probe the interior of a planet. Like, you know, when you need to go to the hospital, when you have a broken bones, we're going to use X-rays to probe the interior of your body. We're going to use here seismic waves to probe the interior of the planet. So here you have what we call the 3D tomographic image of the Earth's interior. And you see in red regions where seismic waves travel slower than an average value, and in blue, seismic waves that travel faster than an average value. And you see we can map in 3D the structure to reveal the interior structure of the Earth's mantle. So here, this video focuses on the interior structure of the Earth's mantle, but we can actually do this for the Earth's core and the Earth's inner core. And so this is a state-of-the-art seismology that we can do for the Earth. You may know that we are currently doing this kind of imaging, not in 3D at this specific level, but at, let's say, lower resolution for Mars. We send rover, we send a seismometer at the surface of Mars, and the idea is that ultimately we would like to build the model that I've just shown for the structure of Mars. We also have some seismometer at the surface of the Moon. So just to let you know that what we are currently doing for Earth, ultimately we want to do this for other planets. But hope I've convinced you that from this zero order description that we have and that we learn in high school, actually in the research community, we now have access to a much more higher degree of description. We're going to see in a second that we want, so this seismic picture actually does not tell us much in the sense that it just tells us that in some region, seismic waves travel faster than the average, and in other region, it travels slower than the average. But it does not tell us anything about the composition. Is this rocks? Is this solid rocks, molten rocks? So to do this, we have to combine this with some kind of physics and geochemistry. And we're gonna talk a little bit about this right now. So let's go first to the first order composition of rocky planets, or the first order composition of the Earth. This is actually an analogy that a professor used when I was doing my master degree, so that we can remember the composition, the average composition of the Earth. So I did my study in France, and Brittany, or Bretagne in French, is a very strong region in France. And you may know this cake that is called a 4/4 breton, or like 4 quarters of Brittany. Yeah, I don't know if the translation is really good. Anyway, so 4/4 means 4 quarters. And in a 4/4 breton, you have basically 1/4 of butter, 1/4 of flour, 1/4 of sugar, and the rest is eggs, 4 eggs. So this is a recipe for a 4/4 breton that is very good with coffee, if you like coffee, or tea, actually. So the composition of rocky planets in the solar system is very similar to a 4/4 breton. You have 1/4 of iron, 1/4 of oxygen, 1/4 of silicon, and 1/4 of magnesium. So at zeroth order, this is how we can describe the composition of a rocky planet. You put actually all the iron, almost all the iron in the core, almost all of it, not all of it, all of it, but almost all of it in the core, and the rest will compose the mantle. So this is a zeroth order description for the composition of the of rocky planets. Why do we have this composition? Because again, we can the ultimate idea is to project or transpose the rationale behind these two exoplanets. We actually have this composition because this ratio, or the relative abundance of magnesium, silicon, iron, and oxygen, has been built in the earth, in the sun. Sorry. So we all come from the sun. So the relative proportions of atoms that we found in the solar system actually reflect the composition of the sun. So this is something that has been recognized actually quite early on. So here I have a figure that has been adapted from an initial paper that dates from 1929. The idea here is to compare the composition of the Earth with the one of meteorites that we believe form the building blocks of planets. And yes, no, actually, sorry, my bad. This plot is the composition of the sun that we compare with the composition of the meteorites. And then we have done the same exercise by comparing the meteorites with the composition of the planets. But here is just to show you that the composition of the meteorites actually match very well the composition of the sun. When I say the composition, you should keep in mind the relative abundance of those atoms. As you may know, the sun is made mostly of hydrogen and helium. There is not a lot of magnesium, silica, but the proportion of magnesium relative to the proportion of silica that we have in the sun is the same as the one in meteorites. So here you see that, for instance, so we have normalized everything by the composition of the sun. So if an element, so we're going to focus on the silicates here, for instance, or maybe you can see my mouse, yes. The silicates here, you see magnesium, silica, it's 1, meaning the composition of the meteorite matches the one of the sun for the silica. And you see it's actually true for many other elements. So here you have not the entire periodic table, but close. Volatile elements that would compose the atmosphere. So you see it's relatively close to the one of the sun. So that means we can have in mind that rocky planets beyond our solar system, they should look like their star in composition. Okay, so now let's move to the highest degree of description when we want to describe the composition of rocky planets. Something very important that has been recognized by geologists or geochemists is that the Earth's interior, and actually this is true for other rocky planets in our solar system, is not homogeneous, meaning these bulk compositions that I just described, it's not the composition that we find everywhere at the surface of the Earth. So this is why we have, for instance, what we call different geological regions. If you move from one place to another on Earth, you will not find the same rocks. You will find similarities, but not necessarily the same. So here, these plots, no need to, I won't have the time to describe all the details of these plots, but there is basic things that can be understood very easily. Here we compare the compositions of different lavas that erupt at different locations on Earth. So here you have, for instance, Hawaii. This is one specific kind of volcanic activity that we called intraplate volcanisms. We have Morb, so this is mid-ocean ridges basalt. So this is lava that erupts and reach the middle of the oceans. And they are found at the middle of the oceans and this is what is responsible for the creation of a new crust. You have the continental crust, so rocks that that would compose the continents, and other what we call geochemical reservoirs. The point is that when you look at the compositions of all those different lavas, they are not the same. So here we have normalized the composition of those different lavas by the relevant composition for the Earth's mantle. So here this is one. So this is the primitive mantle. And you can see that for those elements, so we have magnesium, silica here, iron, and all other elements that we use to distinguish rocks. You see that they are not the same. So this is a strong indication that the Earth is not homogeneous. Some lavas would have a specific composition because they come from a specific location, maybe in the Earth's interior, and this specific location might have a specific composition. So now I'm showing you the interior structure of the Earth's mantle as seen by geochemists. So you can imagine that the ultimate goal is that this picture should match the one of the seismologist. Here in this picture, you see mid-ocean ridge basalt. So this is the surface of the planet. Below the oceans would have a specific compositions. Here they have depicted deep region in the mantle that might have also a specific compositions. So I won't go into the detail of this, but I just want you to keep in mind that the geochemical pictures of a planet might not be the same as the seismological pictures. When those two pictures will match, this would mean that we understand completely the interior dynamics and evolutions of planets. Okay, so now let's move to the dynamics. So until now, we describe the interior structure of planet like something that is very static. And as you can imagine, it's not the case. You know, they are, as you know, at least on the surface of the Earth, we have tectonic plates that move with time. We have the formation of mountains. We have volcanic activities. So everything is actually in motion. So time scales of those motion is really long. You know, the velocity, the typical velocity of a tectonic plate is centimeters per year. It's not very fast, but it's still something that we can appreciate on a long time scales. So now I'm going to describe briefly the essence of dynamics for rocky planets. And where I'm going to distinguish mantle dynamics from core dynamics. So for mantle dynamics, what drives the motion is what we call thermal buoyancy. We have motions because heat that is stored in the interior of planets wants to escape by some heat transport mechanism. The mechanism that would be responsible for transporting heat would be convection. Like convection in the atmosphere or convection in the ocean, we have convection in the Earth's mantle. But the time scale of those motions is extremely long. As I mentioned, it's about the typical velocity for the mantle is about centimeters per year. So what would drive the motion is because the Earth's core is hot. So materials here at the top of the mantle would be hotter than the one at the surface of the planet. Due to the thermal expansion of rocks, materials that are hotter, they are less dense. So they would tend to actually float or at least move towards the surface. And this is what would create convective currents. And this is what would create some region with volcanic activity. This is what would drive the motion of tectonic plates, etc. So at first order, this is how we can describe the dynamics of the Earth's mantle. So now I'm going to show you a state-of-the-art picture of mantle dynamics. This is actually a video that is specifically designed to reproduce the behavior of tectonic plates at the surface of the planet. So on the left side, you see the tectonic plates in a kind of white, and in the middle, between those tectonic plates, you see magma that arrive at the surface and forms new plates, oceanic plates. And you see there is a kind of complex motion due to the spherical shape of the planet, etc. On the right-hand side, you actually see the motion within the Earth's mantle that actually drive the surface dynamics. So just to give you an idea, these kind of simulations take few months to run, actually maybe 6 or 8 months. So it's extremely time consuming because the challenge is that rocks are very weird materials and convection involves the deformations of rocks, and the way rocks deform is extremely complex. So if you want to go beyond this first order description of mantle dynamics based on convection, you need to account for the complex behavior of rocks. This is what takes time in these computations. So this is what the interior dynamics of the Earth would look like on, so here's the time scale. You can see the time scale at about, let's say, 200 million years. This is about the age of the oceanic floor actually on Earth. So 200 million years. It's relatively long, but it's quite short compared to the age of the Earth or the age of the solar system, that is 4 billion years, 4.4 to be exact. Okay, now let's move to the dynamics of the core. So the dynamics of the core is slightly more complex. We still have buoyancy forces that would drive the motion. This is what would be at the source of the fluid motions. So now, just to make sure we're on the same page, we are talking about motion within the metallic part, the metallic shell of the planet. So the fluid that is in motion is liquid metal in the outer core. We are not quite sure if there is actually motion in the inner core that is at solid state. Some studies show that maybe we have a solid state convection in the solid core, but we know for sure that we have liquid state motion in the outer core because this is what would drive the magnetic field. And as you know, the magnetic field is a very important ingredient for the Earth as we know it on Earth. So when we want to then extrapolate this concept to exoplanets, we want to know whether an exoplanet can actually sustain a magnetic field so that it could harbor life there. So what is the dynamics of the dynamics of planetary cores work? So we have buoyancy forces that will drive motion, but the main difference is that since the motion occurs within a liquid material that has a really low viscosity, that means it's very easy for this material to deform, we have other forces that becomes important. For instance, rotation of the Earth becomes extremely important to describe the fluid motion of the cores. This is something that actually is negligible for modeling mantle dynamics. And actually, I should have said this first. Maybe the most important aspect is to actually combine or connect fluid motions with magnetic field generation. This is what we call magneto-hydrodynamics. This is something that is done also for the sun when we study the magnetic field produced by the sun. Actually, it's a similar code. It's really a similar community that studies magnetic field generation in planetary cores. So this was a quick overview of the interior structure, composition, and dynamics of planets. Now I would like to share with you some important questions that we have actually in the field, because they are actually very basic aspects of planetary, of rocky planets that we don't understand. For instance, we don't understand why the Earth is the only planet with tectonic plates. And some people who actually study life in detail might argue that plate tectonics could be a key component of life because it allows to boost interactions between the interior and the atmosphere, or at least the surface of the planet, to boost cycles of different elements or nutrients that are required for life. So some people might argue that we need tectonic plates to have life. So why though the Earth is the only planet to have tectonic plates? Because we don't have this on Mars. On Venus, we have a weird kind of surface dynamics that I don't have the time to explain here, but the Earth is really the only planet that we know that has tectonic plates. Then we have other actually quite simple features that we do not know how to understand properly. The fact that the lavas that we observe at the surface of the Earth, but also Mercury, the Earth's moon, and Mars, those compositions change over time. So if those compositions might affect the surface environment, we should be able to predict those changes. We don't understand right now how this works and where those differences in composition arises. Then about magnetic field generations. If we look at our solar system, we have only the Earth, Mercury, and Ganymede. Those are the only rocky planets that currently sustain and generate a magnetic field within their interior. So for instance, Mars does not have a self-sustained magnetic field, nor Venus. So again, if you want to think about life and having in exoplanets, and we want to have a magnetic field that can protect the planets from stellar radiations, we want to understand in which condition we can have a magnetic field. And now the last question that we're going to use for transition for the next part is, should rocky exoplanets be different from rocky planets in our solar system? So if you are interested in the philosophy of science, or the intersection between science and the history of science, there are some kind of arguments that you can use, that the Occam razor. So as long as you do not know much, the most simple assumption is always the best. And the most simple assumption is to say that until I see something different, I'm going to assume that it's the same. As I believe you can understand, this might not be satisfactory for many of us. So let's move to our next part now, where I'm going to talk about lava exoplanets. Those are a specific kind of rocky exoplanets. And I got interested in those 2-3 years ago when I moved to Canada for my last postdoc before I got my position here at York University. And I'm going to explain a bit this specific class of planets in the context of this new era that we are currently living with the James Webb Space Telescope, because the idea is to constrain maybe the interior structure of a lava exoplanet based on GWST data. So first, I would like to maybe describe a bit more what are those lava planets, lava exoplanets. So here, you're going to see in a second a plot that will take the full page, but I've decided to restrict a little bit this plot so that you understand what it means. So you have here on the horizontal axis the semi-major axis. So we are describing here the structure of the solar system, or the architecture of the solar system. So we have Mercury that is located at about 1.3 AU from the sun. The Earth is there, and you have Venus there and Mars. So this is, until we observed exoplanets, this is the typical architecture for a solar system, for a planetary system. And it's the typical architecture because this is the only one that we know. So you have here on the left some kind of legends to get an idea of the size of the planet. So here, this dot, the size of this dot correspond to this one. This corresponds to the side of the Earth. So R with this cross here means 1 Earth radius. The thing with the exoplanet science is that we have observed now many planetary systems. Here, I've just picked a few of them. I refer you to this paper where you can find actually a lot of those planetary systems that has been observed that showed that the architecture of our planetary system is not necessarily representative of at least planetary system in our neighborhood with respect to the galaxy, to our galaxy. So here, look, we have found many planets that actually orbit very close to their star. So here you see this system of planets. We have 4 planets that orbit at within 0.1 AU. To give you an idea, a year at 0.3 AU, I think it's about 10 days. So Mercury, the orbital period of Mercury, it's about 90 days, 88, I think. And here, when you move to those distance, the orbital period becomes about 10 days. You have here, so this is the first thing. The second thing is look at the size of those planets. So those planets are actually already larger than the Earth. You have those ones here that are significantly larger than the Earth, and they might be actually sub-Neptunes. Well, either super Earth or sub-Neptunes. The second point I want to make is that we have here on the right-hand side a legend for the temperature that is the predicted equilibrium temperature at the surface of those planets. The closer you get to the star, the more radiation by surface area you will receive, so the higher the surface temperature will be. And you see you have those planets here that orbit so close to their star that the surface temperature is actually higher than the melting temperature of rocks. So if those planets have a density of a rocky planet, we call those planets lava worlds. They are what we call ultra short rocky planets, ultra short period, rocky planets, because they orbit extremely close to their star. And they are so close that their surface temperature is extremely hot. So this is the kind of planet that I got interested in and that I'm studying for 3-4 years now. So it's relatively recent in my research. So a few more things about lava exoplanets. So most of them are super Earth-sized planets. So they are larger than the Earth. So we are talking between 1 or 5 Earth masses. There is something very interesting in that you can show from orbital dynamics that planets that orbit so close to their star, they must be tidally locked, meaning that it's always the same hemisphere that faces the star. So it's like the moon, the relation between our moon, the Earth's moon, and the Earth, we always see the same face of the moon. So this is the exact same thing here, the same dynamics. But here, the hemisphere is so close to the star that it will be blasted by stellar radiation. And this temperature of, so I mentioned just before I showed you a temperature of about 800 K, is actually not only high enough to melt rocks, but also to vaporize rocks. So we believe that on lava planets, we might have actually an atmosphere made of rocks. So it's really rocks at the vapor state that might be on the day side of those planets. And again, yeah, we are talking about ultra short period planets. So those actually lava planets orbit not only within 10 days, but we have a lot of them within 1 day. So the orbital period is actually a few hours. We have them, I think we have actually some of those lava planets that have orbital period of about 6 hours, 10 hours. So they rotate very fast. So, as you may know, we are living also in exciting periods because we are lucky to have fairly advanced telescopes. And James Webb is probably nowadays the most advanced telescope that we have in space to study galaxy and planets. It turns out that actually a relatively small fraction of GWST time is dedicated to planets. Originally, it was mostly developed to study, to do cosmology, to study stars, galaxies, etc. It was planned to study planets, but my point is that there is only a small fraction, maybe 15%, 20% of GWST time, I might be wrong, that is actually dedicated to the study of planets. But this GWST, this is what will allow us to characterize, for instance, the composition of planetary atmospheres, because we need to have a very accurate spectrograph to measure, to maybe identify the specific chemical species, and this can be achieved by James Webb, hopefully in the near future, if it's not currently done. So the idea of the research that I'm going to propose is to actually to use maybe James Webb to constrain the interior structure of lava planets. And so I won't have the time to go into the details of this, but this is the model that I've proposed recently that is based on fairly advanced fluid dynamic simulations that I do not have the time to describe here, but you can have a look at the paper that has been published this summer, where we actually propose that we can find lava planets in two different states. So you have on the left side the hot state, and you have on the right side the cold state. I mean, relatively cold. So you always have on those two states on the left side, the day side. So this side is blasted by stellar radiation. But the point I wanted to make in this paper is that it's not because the surface is molten that the interior is also molten. Because this equilibrium temperature only tells you about the surface, not about the interior. So you can show this by doing some kind of calculations. Anyway, so we suggested in this paper that we might be able to find lava planets in two different states. Why would this be important? Well, for two reasons. First, we said that if the interior lava planet is molten, you can show with fluid dynamic simulation that everything will be well mixed. So the composition of the interior will be homogeneous, and the composition of the atmosphere will reflect the one of the bulk planet. So if we wanted to probe the bulk composition of the planet, we want to look at this kind of lava planets. How can we tell if this is in a molten state? We showed in the paper that we can look at the heat flux that comes from the night side of the planet. When the planet is mostly liquid, it can transport a lot of heat towards the night side, and we can actually measure the thermal radiation that would come from the night side. But if the lava planet is in a cold state, we can show that the composition of the liquid magma ocean here would be very different from the one of the bulk interior. It's kind of similar to what I've shown when I described the composition of the lava that erupt at the surface of the Earth. They do not necessarily have the composition of the bulk mantle. And so the composition of the silicate atmosphere that would be in equilibrium with this magma would also be different and not representative of the one of the bulk interior. So if you want to look at the bulk composition of the planet, you don't want to measure the composition of those kinds of very fractionated atmospheres. Or we can tell that this is probably a cold state. We can look at the night side thermal emission, and in that case, it should be low. So with this idea, we have been awarded 100 hours actually of GWST time to actually test this hypothesis. And we would actually study a population of six actually lava planets, and to try to figure out if we can distinguish lava planets in the hot state or cold state. So this is the end of my presentation. I hope I convince you that rocky planets are really fun. There's a lot of things that we can do. It's extremely exciting to study those in this time where we have a lot of new data, where now, as I mentioned, geologists, geophysicists have to interact with astronomers. And something that I would like to mention, maybe until now, the idea was to use our knowledge on our solar system to maybe predict the interior dynamics and evolution of exoplanets. Actually, I believe that maybe in the future, that's going to be the other way around. There are many questions that we have in our solar system that we might be able to answer from data from the exoplanetary science community. So yeah, that's it for me. I will be happy to take any of your questions.
Oh, wonderful. Thank you very much, Dr. Boukaré, for this great talk. That's been really fun. I completely agree. Planets rock and Earth-like planets even more so. Um, sounds like you have a whole slew of wonderful geological mysteries to solve. And I'm sure that everyone who's ever read Journey to the Center of Earth by Jules Verne or anything else is getting very excited about this. So just remind our viewers, if you're on YouTube Live right now, make sure to put your questions in. We'll transfer over to the question and answer portion here. So we'll be taking your questions live for as long as we can pass them through to our speaker tonight. And it looks like we actually have the first question. So here we go. I'm going to go ahead and start the questions from YouTube. So I guess keyboard folks, make sure to type those in. Your first question has come live from Guyana's 6949. And the question is it possible to infer the presence of plate tectonics on exoplanets by analyzing atmospheric signatures that reflect mantle or core interactions?
Whoa, this is a very specific question, a very good one. Can you hear me? Yeah, I believe it works. Okay, good. It's an excellent question. This is actually something that people are trying to test. The challenge is, first you want to make sure that you can have a clear signature in the atmosphere from some kind of tectonics. So that means on Earth, this is where you should try first your experiment. Can you actually really tell from the atmospheric composition that you have tectonics, plate tectonics? It might not be that easy, but let's say you can do this. That means you can identify some specific species in the atmosphere that would reflect this process. And so then the challenge would be, can you actually detect for sure those species in exoplanetary atmosphere? So then it would become a technical challenges. Can we see, the peaks in the spectrum that would come from the light from this atmosphere that would be specific to a given element, or given molecules actually? It might be challenging, but conceptually, this is an excellent idea. And yes, people are working on this.
Wonderful. I'm actually really excited to find out the answer too. So hopefully you folks solve it. Now we've got a few more that have wandered in on YouTube. We have a comment from Crispy Critters, which is at. He says, "Very interesting. Thank you." So just so you know, everyone's very happy with your talk.
Thank you.
And then we have a question after that from Eric Brigg, who asks. It looks like he has a few questions in mind because he asked, number one, are these transiting exoplanets that will be studied with JWST, and is it possible we've heard their designations?
What do you mean by their designations?
So if people want to go and observe these transiting if they're transiting exoplanets, we could potentially go and observe them. So what is their names?
Oh, their names. So since I was in charge, I can, if there is a way to then post the name in the YouTube channel, I can send you the name. I don't remember the name by heart. They have weird names, and I was more in charge of the scientific case, so the physics of the interior. I work with a lot of actually astronomers who work on the data, and they know those names by heart. I don't, but I can definitely send you those names. There is, well, I know at least one. There is K241b for sure. I think there is TOI 44 something. Yeah. Anyway, I can send you those names.
Excellent. So we can probably get those added to either the description of this video or into the comments later after
Yes.
you found them and emailed it to us. Um, so very exciting for exoplanet hunters, I suppose.
Yes.
It's always fun to try to find those transits yourself whenever you can. Now we've got another question who's come in, and I guess folks have started labeling them. So this is from Ralph Chu, who says, would your observations be able to detect earthquakes, in quotes, on your target planets?
Unfortunately, I don't think we have ways to connect some kind of characterizations of exoplanet with earthquake or earthquake, planetary quakes. I don't know how to call them. I don't think we can do this, at least directly, maybe indirectly. So we can go back to the first question that we had. Tectonics is always related to some kind of seismic activities. So if you can probe tectonics, that would be huge first. If you can do this, that would be enormous for the community. Then indirectly, this would be an indication for seismic activity. But can we detect seismic activity independently? I don't think we can do this right now, but who knows?
Yeah, I think that gravitational wave measurement is well beneath the threshold
Yes,
of detection.
unfortunately.
But I do remember how excited everyone was when we got the first signal of Mars quakes. And it is really really exciting to get that kind of geological information from other planets just because it is so hard, right? Um,
Absolutely. No, this
uh,
was, yeah,
yeah.
this was
Great
huge.
stuff.
Yeah.
All right, so it looks like we might have time for one more question. I'll just wait a second to see if anything comes in from YouTube. If not, I might sneak an extra question in myself just for fun because I'm a big planetary sciences fan and a big fan of Jules Verne. So one of the great things that always comes up with these kinds of planetary crust studies is comparing, for example, Earth's crust versus other planets. And if you were going to have um, habitable regions underneath your crust, as in the sci-fi story
Yeah.
Journey to the Center of the Earth, what would you put your bets on, Earth or Mars?
Good questions. I would put like some bet on Mars because I would like to drive some research toward this kind of findings, because it would just be huge to be able to find life on Mars. But yeah, this is what I would do. I would do Mars.
Well, I'm happy you picked Mars because obviously that's my favorite as well. I'm also happy you remembered to wear my planet shirt today. So, well, I think that's it for the questions from YouTube. If folks do come up with more questions later, feel free to post them into comments. And as mentioned, we will try to find those planet names and post
Yes.
them in later. So I'm going to thank our speaker once again. Thank you, Dr. Boukaré, for joining us this evening. It's been great to hear your research talk, and it's been really, really fun. So we're going to go ahead and end off the session for the last session of 2025. I had to check that. Not 2026 yet. It is still 2025. So this is actually the last transfer of the year. of 2025. So this is normally the part where I would hand over to the president of the RASC Toronto Centre RASC, but I am going to slightly co-opt it just a little bit because this is actually my last broadcast with RASC Toronto Centre as second VP, as I won't be continuing in 2026. So I just wanted to take a sneaky last 30 seconds in the broadcast to spend a special thank you to RASC Toronto Centre members who have helped me so much as a second VP, and especially Scott, Tom, Ralph, Lucy, Kirsten, Charles, Mahesh, Andrew, Betty, Ward, and Ego. Thank you all so much. Now, instead of sending it over to Scott, because he's actually not in this evening, for the very last part of the show today, I just want to remind everyone that instead of going through the whole set of announcements, I am going to just tell you about the very most recent ones for this coming month. Now, we have just a couple things coming up for the RASC Toronto Centre that I hope you all will try to attend. The first one is our next recreational astronomy night, which is December 3rd. And I've brought up the site here, so hopefully everyone is seeing that okay. December 3rd will be the RAN recreational astronomy night, and it will not be at York University in person. It is actually going to be online, much like the speakers night, because we also have a special members meeting coming up. So the members meeting will also be online, and if you are a RASC Toronto Centre member, you'll want to log in and go ahead and click that you are attending that so that everyone knows you're coming. If you are a recreational astronomy night fan, just come back to YouTube. And if you're interested in any of our other events, please see rascto.ca/events, and it will pull up all the events for the rest of this year and possibly next year as well once it gets updated. So that's rascto.ca/events. Now, as that is the official end of the show, I will thank everyone again for coming to RASC Toronto Centre for the last speakers night of 2025. Thanks to everybody. Have a wonderful evening and hopefully some clear skies tonight.